Welcome to Purdue University's Project Legacy. Project Legacy's customer is Dr. Buzz Aldrin. The professors in charge of this project are Professor James Lunguski and Professor David Minton. The project manager for Project Legacy is Trevor Jan, and the assistant project manager for this project is Michael Young. What you see here is a visual representation of NASA's vision for missions to Mars. Dr. Buzz Aldrin has his own vision for missions to Mars, which involves two Mars Cycler vehicles. A Mars Cycler vehicle is a spacecraft that will orbit between the Earth and Mars every synodic period, allowing for crew and supplies to hitch a ride to the Red Planet. If we compare the two plans, this yellow rectangle is where Project Legacy comes in. Project Legacy serves as an analog for missions to Mars. Key systems will be tested, methods will be perfected, and experiments will be conducted in order to prepare for missions to Mars. In order to understand why the Moon is a good analog for Mars, it is important to understand the differences between the two. The Moon is much closer to Earth than Mars, putting it within easy reach. Ice deposits are on both the Moon and Mars, temperatures are comparable, effects of isolation on the crew, and comparable levels of radiation are all very similar. Project Legacy is driven by many requirements. This slide outlines some of the broad top-down requirements for the project, including the minimization of initial mass in low Earth orbit or MLEO, supporting a crew for 2-year periods, radiation must be shielded within NASA parameters, and the project must prepare for the colonization of Mars. Our first priority is to figure out on the Moon where we will be building our base. This slide shows a picture of the lunar surface with the North Pole at the top of the image and the South Pole at the bottom. The North and South Poles, highlighted in yellow, are our first areas of interest because volatiles remain trapped in the lunar regolith. The volatiles are expected within about 10 degrees of the poles. The area highlighted in the yellow circle is the South Pole Aitken Basin. The basin is one of the oldest features on the Moon, making it a significant place of interest to scientists. Building our Moon base within traveling distance of the South Pole Aitken Basin is a priority. The South Pole Aitken Basin is closest to the South Pole. The image shown on this slide is of the South Pole. Our Moon base will be located at KBS Crater, see blue arrow. We have chosen KBS Crater as our base site because not only does it meet all of the previously mentioned criteria, but it is also the location of the 2009 LaCrosse missions. The LaCrosse missions tell us exactly what to expect in the lunar surface in KBS Crater, therefore we know that there is the presence of volatiles. We will now be discussing the infrastructure which will be put in place in order to enable the survival of the crew on the lunar surface. This slide shows an overview of Project Legacy. All major components are labeled in this image. Project Legacy incorporates many different vehicles in lunar orbit. The exploration module is the midpoint for the crew between Earth and the Moon. The crew will arrive at the exploration module in an Orion capsule and service module, see left side of the picture, pass through the exploration module, see center of the picture, and then travel to the lunar surface via the ferrying lander, see right side of the picture. Project Legacy also uses 3 communication satellites in order to achieve continuous high-definition communication between the Earth and the lunar surface. One of the biggest problems facing astronauts living on other planets is radiation. Radiation comes from one of 2 places in space. It comes from both galactic cosmic rays, which originate from outside of the solar system, and from solar proton events, which originate from the Sun. Unlike Earth, the Moon does not have a magnetic field, meaning that we have to design our own radiation shielding. This diagram shows a cross-section of one of our 9 habitats. Each habitat has 3 floors. In order to deal with the radiation on the Moon, we will be burying the first floor of each habitat, and covering the rest of the habitats with sandbags filled with lunar regolith. Burying the first floor of the habitats does not only provide radiation shielding, but also stability for the habitats. Stability is important in dealing with moonquakes. Another approach to radiation shielding could have been to bury the habitats completely, however, this requires too much infrastructure. We still need to move enough lunar regolith to bury the first floors. In order to dig the holes for the habitats, we will be impacting the lunar surface 3 times simultaneously. This will be done with a lunar impact vehicle which will be launched from Earth, and separate into 3 smaller impact vehicles before impacting the Moon. It is important to note that these impactors are kinetic, meaning that they do not use explosives. They do, however, cut construction time down by well over 100 days in comparison to the next best option for moving lunar regolith. The image provided shows the impact vehicle before and after separation. This shows all 9 habitats sitting inside of the craters made by the impact vehicle. The 9 habitats consist of 2 living quarters, 2 recreation and exercise habitats, waste and water management, a laboratory and workstation, a medical bay, and 2 food and aeroponics habitats. Here you can see the inside of habitats 1 through 5. Here you can see the inside of habitats 6 through 9. Looking back at our project overview. We will now be discussing the in situ resource utilization system. The system consists of a fuel depot, ferrying landers, and its own rover system. The ISRU system is located 17 kilometers southwest of the base. The ISRU is inside what is called the permanently shadowed region. A permanently shadowed region never sees the light of day. Volatiles that we need to make rocket fuel for our reusable ferrying landers remain trapped in the lunar regolith in the permanently shadowed regions instead of sublimating out in sunlight. This is an illumination map of the South Pole to give you an idea of what these regions look like. The black spots are permanently shadowed regions. The ISRU rover works by digging a hole with the boring cylinder into the lunar regolith, followed by emitting microwaves down the hole, forcing water to sublimate to the surface, where it will be collected using a cold trap. The rover will then transport the water to the fuel depot, where it will be separated into liquid hydrogen and liquid oxygen. The fuel depot is located in the permanently shadowed region, because it requires extremely cold temperatures to keep hydrogen and oxygen in their liquid states. The cold temperatures in the permanently shadowed region makes temperature regulation easier. The reusable ferrying landers will be refueled using the fuel from the fuel depot. The ferrying landers will be used to bring the crew to and from the exploration module. Looking at the overall scope of the project, we will now be talking about the 2 pressurized rovers for use by the crew. The pressurized rovers are a modular system, allowing them to perform many different functions including transporting fuel and resources, moving crew, and assisting in base construction. Not all attachments are shown here. Science and exploration are both big parts of Project Legacy's agenda. The South Pole Aitken Basin is one of the oldest features on the Moon. Analyzing the iron oxide deposits allows us to establish a benchmark for the age of the Moon. Sample return missions will be carried out using 3 science rovers. Science probes will also be used to monitor lunar seismic activity. Final considerations. The Project Legacy timeline ends with the first rendezvous with the Mars Cycler in the year 2035. In order to accomplish the rendezvous with the Mars Cycler, Project Legacy has created a ferry to Mars Cycler vehicle. The vehicle will be launched from Earth using an SLS Block 2B cargo ferrying. The vehicle includes a redundant stage for further maneuvers and even the return to Earth in the event of a failed meetup with the Mars Cycler. There are many reasons why Project Legacy is a good proving ground for Mars. These are just a few of them. The system that has been designed to collect and process volatiles, the communication system, the habitat construction, radiation shielding, and food production methods, and the physical and mental health strategies for the crew are all extremely valuable for both missions on the Moon and Mars. Project Legacy's initial mass in low Earth orbit is 4,037 tons. That is 1.8 that of the Apollo program. Apollo was the first and last set of crewed missions to the Moon. The diagram on this slide compares the Apollo program and Project Legacy in terms of Saturn V launch vehicles. The Saturn V was the launch vehicle for the Apollo program. In order to understand the scope of Project Legacy, a comparison such as this is vital. For further information and specifics, please visit our website, see a link in the description below. Our website provides full access to the final report as well as a video summary of the project. Thank you for your time.